Alright, hello class. So in this video we're going to talk about the root test. And the root test is, I consider it kind of similar to the ratio test, in that it's really good at dealing with specific types of series, and specifically series that would be a real pain to try and do with any of the other tests. And mainly, this is for series that are of the form where the entire thing is raised to the k. So, for example, if you have some series where you've got like just a bunch of like k plus 1 over k squared plus k, all raised to the k. And trying to approach this with any of the other series tests would probably not end well for us if we tried that. But this is where the root test comes in, because the root test is perfect at dealing with this, where the entire thing, where the entire term is being raised to the k. Okay, so let's get into it and get to some examples. Okay, so here's what the root test actually says, and you'll notice it's very similar to the ratio test as far as its conditions. In fact, the conditions are pretty much the same. It's more what we're looking at that's different. And this is often why these two are joined together and talked about together, and are considered very similar. So here's the idea. The root test, we're looking at a series. Say A is the series AK. And we're going to let rho equal the limit as k goes to infinity of the kth root of the absolute value of a sub k. Okay, so this is rho. This is a Greek R. Now, I think it's spelled R-H-O, rho. Okay, now we've talked about that before, where it may not have meant much when we were talking about it in terms of density, but here we're using rho strategically, just like we used R strategically earlier, because we're essentially, in the same way, comparing this guy, sort of, to a geometric series. All right, so we'll get to that. All right, so let's get to the conditions. So we have a rho, which is this limit. Now, if rho is less than 1, then A converges absolutely, and thus just converges. If rho is greater than 1, then A diverges. And if rho is equal to 1, then the test, unfortunately, is inconclusive. Okay, so let's look at what's going on here. Similar to how we did last time. So if the limit as k goes to infinity, okay, of the kth root of the absolute value of ak is equal to rho, then after a certain point, right, now this certain point may be maybe term 100, maybe term 1000, maybe term 2. Whatever it is, after a certain point, we'll basically have that every kth root of absolute value of ak is approximately equal to rho. Right? Because eventually they all have to get really close. So after a certain point, all of them have to be really close. So this implies, well, if I just raise both sides to the k, this implies that the absolute value of ak is approximately rho to the k past a certain point. Right, which is going to be real familiar when you take a look at this next part here. So past this point, all right, past this point of no return, if anyone knows that song. So past this point, let's say K is that goalpost point. So past this point, call it K. That's what I want to say, is call it K. Call it the kth term, right? We'll have that AK plus AK plus 1 absolute value plus AK plus 2 absolute value plus AK plus 3 absolute value, on and on and on. Each one of those is approximately, well, from here, rho to the K. So I have rho to the K plus, now here instead of rho to the K, it'd be rho to the K plus 1. This one's approximately rho to the K plus 2. This one's approximately rho to the K plus 3, plus rho to the K plus 4, and on and on and on. Okay, so this is essentially a geometric series that is starting at K. So the absolute value series, right? The absolute value series is going to be, well, it will be the first few terms that come up to K. So it'll be the sum from n equals, and actually I should do like I did last time and call that n. It'll be n equals, let's just say it starts at 1, just to make things easy on ourselves. So n goes from 1 to K minus 1, absolute value an, plus, then, and let me use a approximate, sorry, then it will be the series n equals K to infinity of rho K. So this piece is just some finite number. We don't have to worry about this. And then this is a geometric series. Okay, which will converge provided rho is strictly less than 1. Okay, so that means basically that this series will converge provided this series converges. All right, so what we're basically saying here is that if rho is less than 1, then A behaves, so A eventually behaves like a convergent geometric series. On the other hand, if this is happening, then A is likely acting like a divergent geometric series. Okay, and then once again, if P is equal to 1, or sorry, if rho is equal to 1, then the test is inconclusive. Okay, so let's look at some examples of where the root test is helpful, and we'll just go from there. All right, so let's take a look at this series here. Say we have the series K going from 1 to infinity. A 3 minus 4K squared all over 7K squared plus. All right, so I'm going to want to use the root test here basically because I have the whole thing raised to the K. So this is what usually tells me that I want to use the root test. Because when you set up your row, right, you're going to do row equals the limit k goes to infinity of, it will be the kth root of the absolute value of all this stuff that you have. And actually, we can simplify our notation a little bit here, and we can always move powers outside of an absolute value. So let me do that. Say that it's that to the k. All right, so this will be the limit as k goes to infinity. Now, here's why this helps so much, is because this kth root and the k cancel. And then we'll be left with just the limit as k goes to infinity of the absolute value of 3 minus 4k squared all over 7k squared plus 6. Okay? And that simplifies this so much, because now notice that the highest power of k in the top and the bottom is the same. The only thing we have to worry about is that we have the absolute value. Note that this would normally be negative 4/7, but since there's the absolute value, this will go to positive 4/7. Okay, so since rho is equal to 4/7, which is less than 1, then A converges by the root test. All right, let's look at another one. Okay, let's consider this series now. K going from 1 to infinity of negative 1 to the k plus 1, all times 10k cubed plus k, all over 9k cubed plus k plus 1, all raised to the k. All right, so I want to use the root test here. Mainly because I have this piece here all raised to the k, and remember, when we do this test, we can ignore this whole alternating piece. So you may have thought, if you just saw this out in the wild, that we might want to use the alternating series test, but really, in my mind, it'll be easier to use the root test just because we can apply the root test to this, and we take the absolute value, which just negates that. We don't even have to worry about it. Okay, so if you remember, the rho is the limit as k goes to infinity of the kth root, the absolute value, I'll call it bk here. And so it'll be the limit as k goes to infinity of the kth root of, I'm just going to drop this. This is always positive, so I'm just going to say that this is 10k cubed plus k all over 9k cubed plus k plus 1, all raised to the k. So the root and the k cancel, so this is really just the limit as k goes to infinity of 10k cubed plus k all over 9k cubed plus k plus 1. Isn't that much nicer? Right? So since we have the matching exponents in the top and the bottom, this is going to come out to be 10/9, which is greater than 1. So rho is 10/9, which is greater than 1. So B diverges by the root test. Okay, so I feel like this one's a lot more straightforward than the ratio test. However, its uses maybe are a little more direct, and it might not have as much of a broad set of uses. However, where it's useful is extremely important and extremely helpful. Alright, now I will say, with this example, we'll see that it doesn't just have to be all your terms raised to the k. Could be more complicated than that. Say for this example, our c, which is a series from k, going from 1 to infinity, of 1 plus 3 over k, all raised to the k squared. Alright, so this isn't just raised to the k, however, we can still use the root test. And I really suggest that we do, because when we find our row, right, which is the limit as k goes to infinity, in this case it'll be the kth root, the absolute value of ck. Well, this will always be positive, so we could really drop the absolute value bars if need be. Right, so it'll be the kth root of 1 plus 3 over k to the k squared. So the question is, how does this to the k, or kth root, interact with this to the k squared? And it does so like this. Something to the k squared, that's the same thing as saying that this is raised to the k times k. And that's the same thing as saying this. It's the limit as k goes to infinity. We'll write that part. Be the kth root of 1 plus 3 to the k raised to the k, and then this whole thing itself raised to the k. Right? Because whenever you raise something to a power and then another power, you multiply the exponents. So it's to the k, so what ends up happening is this cancels with just one of these k's. So this ends up being the limit as k goes to infinity of 1 plus 3 over k raised to the k. Now, does this look familiar? Well, hopefully that's our nice little pattern here for exponential. That's going to be e cubed. And e cubed is greater than 1, so c diverges by the root test. Okay, so let's do another one like that. Let's say I'm looking at the series k going from 1 to infinity of k all over k plus 1 raised to the 2k squared. So once again, this makes me want to use the root test. And it's going to be a similar thing because this is really to the 2 times k power. And when we do the root test, just one of these k's is going to disappear. Okay, so rho will be the limit as k goes to infinity, okay, of the kth root of k over k plus 1 raised to the 2k times k. Now, I like to write it this way just to keep things straight in my head. Now, do keep in mind, this squared is only affecting the k. It's not affecting both, the 2 and the k. All right, so these guys cancel. Then we get to the limit as k goes to infinity of k over k plus 1 raised to the 2k. Oh, now how do we approach this? Well, I'll start by showing you the long way, and then I'll show you a trick that can make this a lot easier. Alright, so you might want to skip ahead if you don't want to see the long way. But remember, this isn't, well, I'll get into that in just a second, but this isn't like the E pattern exactly. Right? It's similar, but it's flipped over. Again, that's a the hint to how you could do this a little faster. All right, so what we're going to do is I'm going to take natural log of rho. So ln of rho is going to be, and actually, let me do it this way. Let's call this S sub k. All right, so I'm going to take the natural log of S sub k, which would be the natural log of k over k plus 1 raised to the 2k. And we do that because we can move this down, okay, and get that this is equal to 2k times the natural log of k over k plus 1. All right, so then as k goes to infinity, 2k goes to infinity, and then this k over k plus 1 goes to 1, so this whole thing goes to 0. So this is a infinity times 0 case. So we'll need to rewrite this. So I'm going to move this into the denominator. So I'll have 2 times the natural log of k over k plus 1 all over k to the negative 1. All right, and before I do L'Hopital's rule, all right, so just to verify, this will go to 0, and now this will go to 0. So we can use L'Hopital's rule. Before I do that, though, I want to actually simplify this. This will be 2 ln k minus 2 ln of k plus 1. That'll make the derivative a lot easier to mess with. Okay, all over k to the negative 1. Okay, now we're going to use L'Hopital's rule. All right, so this will be 2 over k minus 2 over k plus 1 all over, now we'll get negative k to the negative 2, and I'm going to simplify this. First, I'm going to turn this back into a single fraction. Right, so this will be 2k plus 2. Actually, let me write it like this. 2 times k plus 1 minus 2 times k all over, and this is negative 1 over k squared. Sorry, I messed this up. 2 times k plus 1 minus 2k all over k times k plus 1. There we go. Then all over negative 1 over k squared. And now I'm going to simplify this and invert and multiply. All right, so the 2k's up here cancels, so this will just be 2 over k times k plus 1. Then when we invert and multiply, I'll move the negative outside, and this will be k squared over 1. So this k cancels with one of these k's, and then this equals negative 2k all over k plus 1. We're almost there. Now we can finally take the limit, since we have matching leading coefficients here. This will just go to negative 2. All right, so it's tough to remember what it is that we are actually looking at. So we have that the natural log of s sub k goes to negative 2, and then we introduce our e. Right, so this implies that s sub k goes to e to the negative 2, which is 1 over e squared. All right, all that work was just to show that this limit right here, the limit as k goes to infinity of this thing goes to one over e squared. Okay, which will be less than 1, so D will converge. Okay, that's quite a bit of work to go through to get to here. So let me show you a much quicker way to do this. Okay, so I've cleared all that other work, and we're back down to just here. This is the limit as k goes to infinity of k all over k plus 1 raised to the 2k. Now, before I did all that work with taking the natural log and using L'Hopital's rule and all that mess, remember what I said? I said, well, this isn't exactly the E pattern. However, it's flipped over. It would be if it was flipped over. So I'm going to use this rule here. If I have a fraction, provided everything in here is, nice, a isn't 0, and I'm raising it to some power, I can flip the fraction over on the inside, provided I negate the power. Well, how does that work? Well, if we distribute that negative to the top and the bottom, say b to the negative p all over a to the negative p, and then use the rule that, well, a negative power means we flip around the fraction bar, so the a would come up as a to the p, and a b goes down as b to the p, and then we can rewrite this as a over b raised to the positive p. We get right back to where we started. So we can flip the fraction on the inside as long as we negate the exponent on the outside. So I'm just going to do that. Here, I'm going to flip the inside and then negate the exponent. All right, and now I'll have that this is the limit as k goes to infinity of, well, when we split this up, this is k over k plus 1 over k, so this will be 1 plus 1 over k to the negative 2k, and right off the bat, I can see that this is my E pattern with a negative 2 in the exponent, which is 1 over e squared, which will be less than 1. Now, isn't that so much nicer to play with than what we were having to do before? So when I told you that you may want to remember that E pattern, this is why. Because on some of these problems with, say, the root test or the ratio test or the limit comparison test or whatever test you're messing with, it could be that you'll save yourself a lot of headache and a lot of time if you know those exponential patterns. Okay? Now again, as we saw before, it wasn't 100% necessary. We could still get to the right answer. It was just a lot more work. Okay? So, rho is less than 1, implying that D converges by the root test. Okay, so here's a series. I'm starting back at A again, where k is going from 1 to infinity of, now we have this square root, or actually kth root of k minus 1 all raised to the 2k. Okay, so this may be a little bit of work here, but hopefully not too much. I'm going to try the root test. So I'm going to take rho, and I'm going to look at the limit as k goes to infinity of, it'll be the kth root of this thing minus 1 to the 2k, and the root, kth root cancels with just the k, and so this is the limit as k goes to infinity of the square, I keep saying square root, the kth root of k minus 1. Now this is what's going to be tricky to figure out. This is k to the 1 over k minus 1. Now I don't know if we looked at this particular example in that previous section, but let's consider off to the side. So consider k to the 1 over k. All right, where does it go? Well, again, I'm going to call this, let's call this b sub k. I'm going to take the natural log of both sides. And I'm going to go ahead and bring the 1 over k outside, because that is essentially what happens. We take the natural log and bring that over. So this is ln k all over k, and this is an infinity over infinity case. Right, so we can use L'Hopital's rule. All right, so we'll get 1 over k all over 1, which goes to 0. Okay, so if the ln of bk goes to 0, and then we bring the e's back in to cancel this out, then we get that b sub k goes to e to the 0, which is 1. And I do believe, now that I've written this out, that we probably did look at this. Okay, so this thing is going to 1. So we have 1 minus 1. So this whole limit here is going to 0. Okay, which is definitely less than 1. So A converges by the root test. Okay, now to help us on the next thing we're going to look at, what I want to show you is if we did this same thing, say that ck was like k to maybe the 2 over k or to some constant over k. So let's say a over k. Right, the only thing that would change if I do it over here, this would be an a, we'd have an a here, right? We'd have an a over k. It would still go to 0. Okay, which is interesting. So the ln of ck, which is a over k times the natural log of k, this still goes to 0 for any constant a. Okay, so that means c to the k, which is k a to the k raised to the a over k, will go to 1 for any constant a. Now this could be a very useful thing when you're looking at the homework, because this particular pattern may show up from time to time. Okay, now the important thing about this is looking at those inconclusive cases. Okay, so for example, if we are looking at two series that we already know how they behave, for example, this is a harmonic series, which is a divergent p-series. And let's say we also look at I here, which is the convergent p-series, 1 over k squared. And we apply the root test to both. Okay, we will get, for this one, our rho would be the kth root of 1 over k. Well, that ends up being 1 over k to the 1 over k, which k to the 1 over k, as we established just a moment ago, goes to 1. So this thing goes to 1. So this is a case where rho is equal to 1, but h diverges. And if we try it again here with our convergent p-series, well, we'll get something similar. So when we apply the root test, we'll get rho is equal to the kth root of 1 over k squared, which when we simplify that down will be 1 over k to the 2 over k. Well, as we established just a moment ago, this thing is going to 1, so this whole thing goes to 1. And here is a case where rho is equal to 1, but capital I converges. Okay, so once again, we see a situation where rho equals 1 can mean anything. Okay, so that just means you chose the wrong test to use, which honestly is not the end of the world. Okay, if you get an inconclusive test, that just means you need to try something else. Now, also, there's the, glaring thing here that we would not likely use the root test for these problems, but this is just to show two cases where the root test does not tell us anything, but we already know how they behave. So rho equals 1 could mean convergence or divergence, just like the ratio test, which is again why we sort of pair them together usually. All right, so that should get you rolling on the homework for sure. I think we've even looked at some of the most difficult type of examples that you will find. And this will bring us to an end of this particular module. And we will start looking now at taking these ideas and then moving them a little further into more useful places. Specifically, what do these things equal? We know that they converge. Can we actually figure out what they are equal to? Now, in some cases, like a geometric series or a telescoping series, we can do that. We would like to do it, however, for more possibilities, more examples. Okay, so that's what we will be getting to in our final module. And we will start rolling on that in the next video. So I will talk to you all then. Cheers.